The Dupuit-Forchheimer assumptions provide the mathematical foundation for simplifying complex groundwater flow into manageable engineering calculations. By assuming that the water table is nearly horizontal and that flow is purely horizontal and uniform with depth, we can derive the Dupuit formula. This approach is essential in geotechnical engineering for estimating the discharge rate of a well or determining the hydraulic conductivity of an aquifer during a steady-state pumping test. In an unconfined aquifer, the upper boundary is the water table, which is free to rise and fall. When pumping occurs, the water table drops, forming a cone of depression. The Dupuit formula for this scenario accounts for the fact that the saturated thickness of the aquifer decreases as you move closer to the well. The discharge Q is proportional to the difference between the squares of the hydraulic heads, expressed as where K is hydraulic conductivity, and H represents the head at radial distances R. A confined aquifer is sandwiched between two impermeable layers, aquitards, meaning the water is under pressure. Unlike unconfined systems, the saturated thickness B remains constant during pumping as long as the potentiometric surface stays above the top confining layer. Because the flow area does not change with the drawdown, the resulting mathematical model is linear with respect to the head, making the calculations slightly more straightforward than those for unconfined flow. For a fully penetrated well in a confined aquifer, the steady-state discharge is determined by the transmissivity of the formation. The relationship between the pumping rate and the drawdown at two observation points is defined by the formula. In this equation, the term Kb represents the transmissivity, T. This formula is a staple for geotechnical engineers when designing dewatering systems for deep excavations or tunnels where artesian conditions might exist. While powerful, the Dupuit-Forchheimer theory has notable limitations. The assumption of purely horizontal flow becomes increasingly inaccurate near the wellbore, where vertical flow components are significant due to the steepening of the hydraulic gradient. Additionally, it ignores the seepage face that typically develops at the well wall in unconfined aquifers. Despite these theoretical gaps, the formula remains highly effective for calculating discharge at significant distances from the pumping source. In practice, these formulas are indispensable for site characterization. By monitoring the water levels in two observation wells, R1 and R2, while pumping at a constant rate Q, an engineer can back-calculate the hydraulic conductivity of the soil. This value is critical for predicting settlement, assessing slope stability, and designing effective drainage systems for infrastructure projects. Choosing between the confined and unconfined formulas depends entirely on the stratigraphic profile of the site. If the equilibrium water level is below the top of a permeable stratum, the unconfined, quadratic, version is used. However, if the water is confined by an overlying clay or silt layer, the confined, linear version is applied. Understanding the transition between these two states is vital for maintaining the integrity of geotechnical designs during long-term dewatering.